Hello, everyone. Welcome back to Mathematical Statistics. We have been talking about ancillary statistics. These are statistics whose distribution is parameter-free. And last time we had a kind of cool theorem that said if you have a sufficient statistic, S, and another statistic, T, that is independent of S, then T is necessarily ancillary. Now, I don't find that I often care about a statistic being ancillary as the end goal, but rather something that's going to help me achieve another end goal. And so this theorem is not all that exciting. It's cute, but to result in an ancillary statistic is not something I usually care about. We would like to be able to sort of go the other way and say that a sufficient statistic, which contains sort of all the information about the unknown parameter theta, and an ancillary statistic, which contains kind of none of the information about theta, I would love to say those are independent, but that's not true. But it is if we throw in completeness. So it's time for Basu's theorem. Suppose that we have x1 through xn IID. Actually, they don't need to be IID, but with a common or not common PDF, f of x and theta. Suppose that S, some statistic made out of the data here, is complete and sufficient. And suppose that T, another statistic made out of the data, is ancillary. Then the punchline is that S and T are independent. Let's prove it. So usually I start off by sort of writing what we have, but it's right there. So my first line of this should be something like, suppose S is complete and sufficient and suppose T is ancillary, but it's right there. So I'd like you to consider the following function of S. I'm going to call it G of S, and it's going to be F sub T of T. Now this is the PDF of the ancillary statistic T minus F, the conditional PDF for T given S, and then plug in T given. And then usually in here we have a lowercase letter. It's just an argument, but I'm putting the capital S in here. And that's what makes this entire thing a random variable. Sure, it's also a function of T, but it is a function of S, and that's the only random thing here. I mean, this is sort of trivially a function of S. It's constant in capital S, but this is random. And therefore, this entire thing is random. And if we want to compute, say, an expectation, we should use the PDF for capital S for our complete and sufficient statistic, because that's the random variable here. Let's do that. Let's find the expectation. So the expected value of G of capital S is the expected value of all this stuff. So I'm going to take the expectation onto each term. The first term has nothing random, so it's like a constant in the sense that it's not random. I'm not saying it's a constant function, but it is not random, so its expectation is just whatever it is, ft of t. And then over here, I want to compute the expected value of this function of s. So these could be discrete random variables, but I'm going to use continuous notation. We're going to integrate minus infinity to infinity. We're going to put that function of s there with a lowercase s. So the conditional PDF for t given s at t given lowercase s, and multiply by the marginal PDF for s. That's how you compute the expected value of that circled function of capital S. Okay, so this conditional PDF is, I don't care what order you want to write these in, but it is the joint PDF for S and T over the marginal PDF for S. And once you write it that way, you're going to get cancellation. So we end up with the marginal PDF for T minus the integral minus infinity to infinity of F S T S and T ds. And when you integrate S out of that joint PDF, you end up with the marginal PDF for T. And so overall, this expectation is going to be 0. To show what we started with. So I took the expected value of a function of S and got that it was 0. Now S is not only sufficient, but complete. And this means that this G of S is going to be 0 with probability 1. So S being complete implies that G of S is 0 with probability 1. You'll recall that doesn't mean the function G is identically 0, but it's 0 for all values that S is going to possibly ever take on. And what was this? G of S was FTT minus FT given S, T given S. So this is going to be 0 with probability 1. And so let me simplify this a little bit and say that let's take the randomness out. This minus this with a lowercase s is 0 for all possible s, little s, that S can take on. And from this, we have that f of t given s, so this conditional PDF, is equal to the PDF for the t alone, as long as this s makes sense, is something that can actually appear when you're making observations of this capital S. And this is how some people, myself included, define independence. This implies that S and T are independent. But if you don't like that, if you're really stuck on the definition of independence where a joint PDF factors into a marginal, then you can get this result by rewriting this. It's a joint PDF. I don't know why I keep writing S then T. It doesn't matter though. Now recall, we are assuming that the little s's we're looking at are the possible ones. So this is not going to be 0. So we can multiply it to the other side. And then you have a joint PDF is the product of the marginals. So you have independence that way as well. But either way, showing that S and T are independent is what we wanted to show. And we are done with the proof of Basu's theorem. It's pretty cute. Let's try an example, a pretty contrived example. As I keep saying, whether or not you're going to actually be able to use this for some real life problem, I think you might one day, but those opportunities are few and far between, but it's going to be awesome when you can. So let's suppose, this is my example. Let's suppose that we have x1 through xn, IID, maybe, let's go say exponential, but let's make this, yeah, all right, I'll just do exponential. Exponential with rate lambda. I want to find the expected value of t, where t is the statistic formed by taking the minimum of the sample over the sum as I goes from 1 to n of the sample. So the expected value of this is quite difficult at first glance. Number one, the minimum is not independent of the sum. But even if it was, if you had x and y independent, that doesn't mean you can say that it's the expected value of x over the expected value of y. If they were independent, you could say that this was the expected value of x times the expected value of 1 over y. Again, only if they're independent, and I'm not writing that there. But yeah, it's not an easy problem at first glance. given that we just did Basu's theorem, it is an easy problem. Check this out. The lambda for the exponential distribution is a scale parameter, right? We're looking for a PDF like f of x and theta that has the form theta times another function that doesn't depend on theta, where you plug in theta x. And that's what's going on with the exponential. This is lambda f naught of lambda x, where f naught of x is the exponential rate 1 PDF. I go throw in the indicator as well. So lambda is a scale parameter. And then t is a scale invariant statistic. Recall that a scale invariant statistic is if you take all your data points, your capital X1 through capital Xn, and multiply by a positive constant c and form the statistic, you'll get the same thing that you would have gotten if you didn't multiply by c. So if I have a bunch of data points and I multiply by a positive constant c, a negative could cause trouble, then everything gets multiplied by c, whether that makes them go up or down if c is, less than 1. But the minimum of the new data is c times the old minimum. And if you sum up c times the xi, you just get c times the sum of the xi. So maybe I should actually write this. If we let yi be cxi, and we want to compute the statistic, the minimum over the sum of the y's, this is going to be c times the minimum x over the sum of c times the xi, and you could pull that c out and they'll cancel, so you'll get the minimum over the sum of the xi. In other words, multiplying by c and forming the statistic gave us what we started with. So it's a scale invariant statistic. This means that t is ancillary. We proved this last time or the time before that if you have a scale parameter and a scale invariant statistic, it is ancillary, which means its distribution does not depend on the unknown lambda in this problem. So because we're right after Basu's theorem, what do you think I'm going to do? We know that t is independent of a complete and sufficient statistic. And if you use one parameter exponential family, I'm not going to write it out. We've seen this before, or if you don't recall it, it's super easy to show this. Get the joint PDF and put it into the right form, and you'll get that the statistic S that is defined to be the sum of the xi is complete and sufficient. So by Basu's theorem, we know that S and T are independent. Now S is right there, and you'll recall T is the minimum over the sum of the xi, which is S. So if you take T times S, you get the minimum of these exponentials. So if you take the expected value of T times S, you get the expected value of the minimum. The minimum of n IID exponentials with rate lambda is another exponential random variable with rate n lambda. And the mean for that is 1 over n lambda. So how does this get us what we want? On the left side here, by Basu's theorem, because T is ancillary and S is complete and sufficient, we get that, we have this independence here. So I should say really by independence, which happened to come from Basu's theorem, we get this. And on the right side, we still have what we have. Now, this is what we're after. So if we can find this, then we can move things around and we are essentially done. S was the sum of, this is really sloppy, I'm sorry about this, but it was the sum as I goes from 1 to n of these xi's, And this is n times the expected value of one of them, just because I pulled the sum through and then they're identically distributed, so I get one of them. This is n times 1 over lambda, or n over lambda. So going back here, we have the expected value of t times n over lambda is equal to 1 over n lambda. And when you flip this to the other side, we get that the expected value of t is 1 over n squared. We get our lambdas canceling. And we shouldn't have any lambdas because we know that t is ancillary. So the distribution of t does not depend on the parameter lambda. And so things that you can compute using that distribution, like its mean and variance and things like that, are not going to depend on lambda. So if I got a lambda in this final result here, I would know something went wrong. But this is the answer. So it's a really sneaky way of computing an expectation for something that is otherwise quite difficult to work with, because the minimum in the data is not independent of the sum of the data. And even if it was, that's still going to be, well, that actually won't be that bad, but they're not independent. And so it is bad to find the expectation of this kind of more directly. Love Basu's theorem. It's now time to go back to hypothesis testing, and it's going to be a lot more general than what we've seen before. General hypothesis testing is going to be my title here. I hope that doing the initial hypothesis testing a while back allowed some of the terminology to sink in, like size and level of significance, alpha, type 1, type 2 errors, because I think the hardest part about what we're going to do is just all the notation and all the language. So for general hypothesis testing, we're going to find that we're no longer restricted to hypotheses with things like equals, not equals, less than or equal to, greater than or equal to. And really, I started to put a dot, but this is all we've done so far. It's all we can handle. We're going to have much more general looking hypotheses, and we are also not going to have to guess at what statistic to use to get a good test. So we know a little bit about what makes a test good and better than another test, but I will remind you of that as we go. So some notation, we're going to have x1 through xn, IID from a distribution that depends on some parameter theta, which could possibly be vector valued. So for every parameter, we have a parameter space. For example, if this theta is the lambda for the exponential, lambda takes on values from 0 to infinity. If it's the p for a geometric distribution, it takes on values from 0 to 1 inclusive. So we have a parameter space, and I am going to denote the parameter space with this kind of capital theta. A few ways of making a capital theta. I'm going to use this one. So for example, this might be 0 to infinity. It might be 0 to 1. It might be, I don't know what other things we've seen, but minus infinity to infinity, like for the mean for a normal distribution. And so that's going to be notation for our generic parameter space. Now I'm going to let this capital theta naught, because it's going to kind of take a role in the null hypothesis. Remember, we use like a theta naught and a theta 1. This is different because this is not a single parameter, but a whole set. But I'm going to let this be some subset of the space. And then before I state our generic hypotheses, I wanted to talk to you about like a set subtraction, or sometimes this is called a set minus notation. If we write theta and then a backslash, theta naught, this is everything that's in theta but outside of theta naught. So it's a complement of theta naught. But if we just write complement, you might screw something up because it's the complement with respect to theta. So this is defined actually as theta intersected with theta naught complement. For example, if we're working with, say, an exponential distribution, I'm going to write theta just so this instead of lambda. Our parameter space is the positive real line. Those are the rate parameters that are allowable. And if we're dealing with a subset like theta naught is maybe 0 to 1, I don't just want the complement of this, I want it with respect to this. So the complement is going to be, this guy is going to be everything from 1 to infinity, as opposed to the complement of this on the entire real line. I made that sound way harder than it is. But this is how we're going to define our hypotheses. So our general hypotheses that we want to start to consider, we're going to have a null hypothesis that says the parameter, which could be vector valued, is an element of or is in this part of the parameter space that we've defined, versus the alternative that says that the parameter is in the rest of the space. Okay, so this is our goal is going to be to come up with hypothesis tests here that meet conditions of being great, better, best, powerful, uniformly most powerful, stuff like that. Before we get started, I guess we are started. At this point, we're going to change our language just a little bit. So we are used to having what you might call rejection rules for a hypothesis test. This might be something like, I am going to reject the null hypothesis if the sum as I goes from 1 to n, I'm just making this up, of the xi is greater than or equal to a chi-squared critical value that cuts off area alpha to the right with n degrees of freedom. This rule is now going to turn into a rejection region or critical region. So over here, critical or rejection region. Rejection region used a lot more in a more data-oriented course, and critical region in usually more theoretical courses. But for a critical region or rejection region, we're going to use a vector, capital X, to denote the data. I'm writing it as a row vector. It's not important. We're not going to be doing like matrix multiplication or anything. And the rule is going to now be to reject the null hypothesis if the vector X is in a region C for critical region, where C is defined to be all of the n-dimensional points, little x1 through little xn, or whatever, these are dummy variables, such that the sum of the xi is greater than or equal to chi-squared alpha comma n. So we're saying the same thing on both sides of the screen here. But by saying it in the second way, by using this critical region or rejection region notation, it's going to allow us to really simplify our discussions ahead. Like if you have two tests and you want to know which one is better, like I am testing something involving an exponential distribution and I made a test based on a minimum and a test based on a sample mean, which one's better? We can talk about two tests rather compactly by talking about two critical regions and comparing critical regions as an equivalent thing to comparing two tests. So I could say test 1 is the test based on the minimum, test 2 is the test based on the sample mean, but then I can continue to talk about them with a very compact notation. Okay, so let's look at some of our old definitions with our new terminology. We had the idea of a level of significance of a test, which I also called the size of the test. And I did say at that point, later, I would hopefully convince you of like why some people use the word size. So we're still going to call this alpha. This is still the maximum or supremum if you're, into that. The probability of making a type 1 error. A type 1 error was you rejected the null hypothesis, but you shouldn't because it's true. And the maximum is taken over all the values in the null hypothesis. So we have a set describing that now. I'm going to take it over all theta in this sort of this subset of the rejection region that describes the null hypothesis. I am throughout today working with these general hypotheses. Okay, so type 1 error, the probability you reject the null hypothesis when you shouldn't. And I'm just going to say when the parameter is theta, and then the when you shouldn't, because the null hypothesis is true, is taken care of back over here, because those are the thetas we're looking at. And I've used this before, this kind of notation I'm using on the next line, but we're really going to start using it a lot now. I don't want to keep writing when the parameter is theta. I don't think you want me to keep writing it either. So this is going to be reject the null hypothesis and then a semicolon theta. And so this is purely notation for the line above. So we don't have to write when the parameter is theta. You'll see some people, some books use a vertical line instead of the semicolon. And I've told you what I thought about that in the past when we started using our notation for a PDF or a joint PDF. Some people use a vertical line there as well. But I think, well, it looks like conditional probability, which looks like Bayesian statistics. If you want to use a vertical line here, go for it. I won't mark you off for that. Okay, so using more of our new notation, this is the maximum over all theta in this region that defines the null hypothesis of the probability that the capital X vector is in this critical region. The test defined by this C. So nothing new here except for notation and language, which is really the biggest part of getting through hypothesis testing. It was before, and now I'm piling on more notation and language, which is, again, why I separated it in this course. So hopefully some of that sunk in the past. Let's look at the power function in our new language. We were calling this gamma. Now, this is not a standard notation. You know, power functions are called lots of things, but it's a function of theta. And this is the probability you reject the null hypothesis when the parameter is theta. So we can say that by just simply writing semicolon theta. And theta does not come from the null hypothesis or the alternative. It's just a function of theta, no matter where it is. And in our new notation, this is the probability that X is in some critical region C that we have defined. And if you're comparing two power functions, I think in the past I've used like a gamma 1 and a gamma 2. But for our new notation, we might use that as well if we have two critical regions, or we might end up just like writing C1 and C2 as a subscript to say that these are two power functions going with associated with test C1 and C2 respectively. So I know I just made this big deal about how everything is getting so general now, and we're not stuck with these simple hypotheses in all senses of the word, in the English language sense of the word simple and the statistical sense of the word simple hypothesis. And yet I'm going to start simple versus simple as a building block here. So hopefully you won't hate me too much. Let's look at simple versus simple as our stepping stone case to developing a best or most powerful test of more general hypotheses. So suppose we have a null hypothesis that theta equals theta naught versus an alternative hypothesis or alternate hypothesis, that theta is some theta 1. just like before when we did hypothesis testing, if these are your hypotheses, then you have to assume these are all the possibilities. So the parameter space, even if it's not true, you're sort of considering it right now to just consist of 2 points. Because you may have examples where neither of these look even remotely true, because these are 2 different numbers and they might look wildly off given what you're looking at the data. So you might think neither of them are true, but you have to stay in the framework of hypothesis testing where you assume the null hypothesis is true unless you can show the alternative is true. So these are your 2 options. Okay. I want to find or even define first and then find the so-called best test. This is like the UMVU for hypothesis testing in the simple versus simple case. It's the best you can do. And let me finish this sentence, actually. I put a period there, but of size alpha or level of significance. So what makes one test better than another? Let's consider 2 tests which are defined by 2 different critical regions, C1 and C2. See how easy that was to describe 2 tests really quickly? I mean, I don't know what they actually are, but it's 2 different tests. Running an example, maybe this is the exponential distribution, and C1 is a test based on the minimum of the data, and C2 is the test based on the sample mean. So if these are 2 tests, I should finish this sentence too, of size alpha, then we know that alpha is the probability the data, this is capital X1 through Xn, is in C1 when the null hypothesis is true, that has to equal alpha. And we also know that you have to get alpha as the probability your data is in C2 when the null hypothesis is true. If we have 2 tests of size or level of significance alpha, then they satisfy these 2 statements. So when can one be better than the other? They can differ. They have the chance to differ when the alternative hypothesis is true. So I want to rewrite these probabilities with theta ones instead of theta naughts. And so let's say that C1, we're going to define right now, C1 is the better test if. So if we look at the probability that X is in C1 when the alternate hypothesis is true versus the probability that X is in C2 when the alternate hypothesis is true, because they're already acting the same when the null hypothesis is true, then what do we want to happen here? I want some kind of inequality. And if you are in the critical region or rejection region, that's when you reject. So this says I'm rejecting using the first test, and this says I'm rejecting using the second test. And in both cases, the alternate hypothesis is true, so we should be rejecting. So if C1 is the better test, then we should have a higher probability of rejecting when the alternative hypothesis is true. So this is how we're going to define a better test if we have the simple versus simple kind of scenario. And assuming we are restricting ourselves to the better test of size alpha, the better test of level of significance alpha. We already have that this is equal to this because those are both alpha. So we're going to start comparing them again when the alternative hypothesis is true. Okay, so staying in this simple versus simple regime, we are ready to define the best test. So suppose I have an x1 through xn with a joint PDF, f of x and theta, and as usual, they're likely IID random variables. And I want to define a best test. So let's say C is the best test of size alpha for the simple versus simple, that theta is theta naught versus theta is theta 1. And maybe you want to call this like C star, it's the best, put a star on it. But actually, if you do that, I would recommend putting it as a subscript, only because the C is representing a region, and we're gonna be taking the complement of this sometimes. So you'll have like C star complement, and it's a lot to sort of pile up in the superscript. Or you could just call it C, because right now we're defining the best test. So I don't need a star until there's other tests to say this is the star one. So two things have to hold here. Number one, it needs to be a test of size alpha. So the probability that the data is in C when the null hypothesis is true needs to be alpha. This is just, it's going to be the best test of size alpha. It needs to have size alpha. And the other thing is, you know what? I want that star. I want that star. So I'm going to put this star in here. Number two, if C is any other test with the probability that X is in C when the null hypothesis is true is alpha. This is a capital C. That means it's another test of size alpha. Then the probability that X is in what we're calling the best test when the alternative hypothesis is true. So this is a rejection. If you're in the critical region, you reject. We want it to have the highest probability of rejecting. So this is greater than or equal to the probability that X is in C when the alternate is true. And the key word here is any, no matter what other test corresponding to the critical region C you can come up with. So best test of size alpha means it has to have size alpha. And then when you compare it to all other tests, when the alternate hypothesis is true, you are rejecting with the highest probability, because when the alternate is true, that's when you should reject. Easy enough when we're talking simple versus simple to understand what's going on there, hopefully. Okay, so still in this simple versus simple regime, how can we find a best test? We find a best test with the Neyman-Pearson lemma. A lemma, is something, it's a theorem, but it's supporting another theorem. And you'll see eventually why we're calling this a lemma. Basically, it's a building block for a best test when we're not in the simple versus simple case. So the setup is I have x1 through xn with a joint PDF f of x vector and theta, and they're probably IID. And I'd like you to consider the ratio. I'm going to call this ratio lambda because lambda is like an L, and this is a likelihood ratio. It's going to be a function of x's. We're eventually going to plug the capital X's in, but right now I'm just writing it down as a function. Semicolon theta naught and theta 1. I'm going to define it to be the joint PDF evaluated at theta naught and the joint PDF using the model with theta 1. We saw this in just the last class. This is a likelihood ratio, because if you've got some constants on your PDF, constants with respect to theta, multiplicative sitting out front, they would cancel in this ratio. So you might define this as like a likelihood over a likelihood. It's going to be equivalent, assuming you defined one likelihood and stuck with it. You didn't drop the constants for only the numerator or something like that. So this is, I've yet to define this test, but it's going to be the first of a bunch of tests known as likelihood ratio tests. And what is the point? Okay, here's the Neyman-Pearson lemma. The best test of size or level of significance alpha for testing the simple versus simple hypotheses that theta equals theta naught versus theta equals theta 1 is, I'm going to give you a critical region right now. So up here, I probably should have said the best critical region, but a critical region and a test are interchangeable. It's our new language. So call it a best test if you want to, but it's going to be C star, and it's going to be defined to be all the vectors X for which this likelihood ratio is less than or equal to a constant K, or C, but there's a lot of C's here, where K is such that we have a size alpha test. So this means that the probability that the capital X's, the data, because that's where probability is, it's not with the lowercase x's, is in C star when the null hypothesis is true. This needs to be alpha. So this is the best critical region corresponding to the best test. Let's look at that likelihood ratio a little bit. You'll notice that I have a less than or equal to here. Some of our tests, we have less than's, greater than, things flip. This is always at least going to start with a less than or equal to, because if you had maybe discrete data where you can interpret the joint PDF as a probability, let's just think in discrete data terms for a moment. This is going to be the probability that x1 equals some x1 out through xn is some xn when the parameter is theta naught, and this is going to be the same thing when the parameter is theta 1. So the numerator of the likelihood ratio is the probability of seeing the particular data, little x1 through little xn, when the parameter is theta naught, so when the null hypothesis is true. And the denominator is the probability of seeing that data when the alternate is true. And if the probability of seeing the data when the alternate is true is larger, that's going to make this fraction smaller. So that's why our rejection rule is always going to say, I'm going to reject the null hypothesis when this fraction gets small, no matter what distribution we're working with and no matter what statistic we ultimately end up working with. That's why this less than makes sense. We're definitely going to prove this, but I think to make it feel a little more concrete, I'd like to start off with an example, and then we'll come back and prove this. Let's try it. Let's go back to our tried and true exponential. Suppose I have x1 through xn IID, exponential with rate lambda. And suppose that we want to find the best test of size or level of significance alpha for the null hypothesis that lambda is some lambda naught versus the alternative hypothesis that lambda is some lambda 1. Now, this is just us being a little bit general about it, but lambda naught and lambda 1 represent numbers, just like they did before. So we should be able to look at them and say one is bigger than the other. So I'm just gonna give this. I'm gonna say where lambda, say 1 is less than lambda naught. Okay, so the PDF, as you know, f of x and lambda is lambda e to the minus lambda x, and an indicator that says that x is between 0 and infinity. And so the joint PDF, because these are IID, we get to multiply, and we end up with lambda to the n e to the minus lambda, sum of the x's, and then a product as I goes from 1 to n of the indicators. This part, as usual, the indicator part, not important until it is, until the parameter is in the indicator, because I'm about to make a ratio of these PDFs and put a lambda 1 and a lambda 2, and this is going to be the same in the numerator and denominator, so it's just going to cancel away, whereas it wouldn't cancel away if this was, say, an interval from 0 to lambda. So let's look at the likelihood ratio lambda of x. All right, this is This is confusing. I don't know why I didn't see that one coming. One thing I can do is just make the whole problem exponential with rate theta, but I'm sort of here already, so hopefully this is not too bad for you. It's a function lambda of the vector x and the constant lambda 1 and lambda 2. It's a little bit weird. But this is the joint PDF with lambda not plugged in over the joint PDF with lambda 1 plugged in. So write this in the numerator with lambda naught and in the denominator with lambda 1. I'm going to go ahead and simplify it without writing those out. Once we simplify it, we're going to get lambda naught over lambda 1 to the n e to the minus lambda naught minus lambda 1 times the sum of the x's, and the indicators are going to cancel for the numerator and the denominator. So forget the fact that we had this whole set thing. This gives us the way to define points in the critical region. But this is the rule for being in the critical region. So let's just look at that. Suppose that we have lambda of x of lambda 1, lambda 2, so the likelihood ratio less than or equal to k. We now know for this example that lambda naught over lambda 1 to the n e to the minus lambda naught minus lambda 1 sum of the x's is less than or equal to k. This is going to be our rejection rule. We're going to reject when someone takes the data and actually computes this thing if it's less than or equal to k. But we want to know what k is. So let's try to get a handle on k by simplifying this. This is going to be equivalent to if I divide this to the other side. Now remember, rate parameters for the exponential are always non-negative, so I'm not going to be flipping anything. I'll get e to the negative lambda naught minus lambda 1 sum of the x's. Right now my x's are lowercase. I'm just doing algebra at this point. If you want them to be random variables, that's fine too. In the end, I will have random variables there. Is less than or equal to lambda 1 over lambda naught to the n times k. This is just another constant because our sample size n is always known, and our lambda naught and lambda 1 is known. So I'm going to call this k1 and not carry around all that stuff on the right-hand side. I'm still working my way towards isolating the x's. So I'm going to take the log on both sides, and it's a nice monotone function. So the inequality will stay where it is. And I'll get minus lambda naught minus lambda 1 sum of the x's less than or equal to the log of k1, which is just another constant that I'm going to call k2. And still trying to get down to those x's, I want to divide by this thing. So here's where it's important that, what did I say? I said that lambda 1 was less than lambda naught. That means that this thing inside the parentheses is positive, and so this entire coefficient is negative. So if I divide, I'll just get another constant, say k3 over here, but the inequality will have flipped. And so the rejection region for this test should have the form reject when this is less than or equal to k, but that is completely equivalent to rejecting when this is greater than or equal to a different constant that I'm calling k3. It's equivalent, and you don't need to keep track of the constants to work your way back up, because in the end, you're trying to give someone the rule to reject for when they get their data. And if you want to say reject when the sum of the x's is greater than this number, or for some reason you want to go all the way back up and say, no, I want you to find the sum of the x's and put together this entire expression and reject if it's less than or equal to this number. I mean, that's equivalent, but I don't really care to do that. So I don't need to keep track of those constants. In fact, I'm also often really messy with this where I just keep calling it k over and over again, even though it's not the same constant. So here is the form of the rejection rule. We're going to reject the null hypothesis in favor of the alternative. if, and now I do want to make sure things are nice and random, capital, the sum as I goes from 1 to n of the capital Xi is greater than or equal to k. I would definitely just call it k. It's just some constant at this point, but I don't want anyone to take me literally if I write k there, because I had a k before, so I'll write greater than or equal to k3, where k3 is determined or chosen to give a size alpha test. Two things have happened here. Number one is it popped a statistic out for us. We didn't have to say, should I look at the minimum? Should I look at the mean or something else? I could definitely look at the sample mean because I can put a 1 over n on both sides of this and it's totally equivalent. But this is telling us the best test is basically going to be that test based on the sample mean. Not only is it better than the test based on the minimum, but any other test someone could have dreamed up based on any other weird statistic. And so it gave us the statistic and it gave us the direction of the test. There was no, okay, if this is large, this is small, therefore I want to reject if this is over here. It does all the work for you. It's pretty cool. Again, if you'd prefer, you can give an equivalent test. You could say, I want to reject if x bar is greater than or equal to some k4, where k4 is 1 over n times k3. Okay, so this is the form of the rejection rule. And watch out on some of your homeworks in this class. I will ask you just for the form of the test, just so you can go through these motions without having to do the extra work of finding the critical values, because this part is nothing new. So, I don't always want to test this again, but we did want to find, I hope I wrote this. Yeah, we want to find the best test, not just the form of the test. So let's keep going here. Let's find the constant. It's absolutely nothing new here. This is the rejection rule. And now we're going to use alpha to find the constant K3. So alpha is the probability you reject the null hypothesis when it's true, which means the parameter is lambda naught. No maximum because it's the simple null hypothesis. Rejection for us means that the sum as I goes from 1 to n of the xi is greater than or equal to some constant k3 that we're trying to determine when the parameter is lambda naught. Okay, if the parameter is lambda naught, this tells us that x1 through xn is IID exponential with rate lambda naught. I just want to say one more time that now there's absolutely nothing new here. Finding the constant is the same as finding the constant always was, but the Neyman-Pearson lemma gave us the statistic we should be looking at and the direction of the test. But if this is true, then that means that this sum of the x's, as I goes from 1 to n, has a gamma distribution with parameters n and lambda. So maybe we give that a name, but we can't find exact critical values for the gamma distribution. If we had actual numbers here, like an actual lambda naught and lambda 1, then maybe you could do this numerically, but we can't integrate the gamma distribution. We can't find CDF values in closed form. So this is perfect for giving a test in terms of a chi-squared critical value. And if you want to turn this into a chi-squared, we need to get the second parameter to be 1/2. And we know that if you multiply by like a lambda, it would end up divided here. And to get a 1/2, we need to multiply by 2 lambda. And so we've got that 2 lambda, sum of the x's, has a gamma n 1/2 distribution, which is gamma 2n over 2 1/2, which is a chi-squared distribution with parameter or degrees of freedom 2n. So let's call this like W. Let's just define that. Alpha is going to be the probability that W Sorry, I can't do that yet. Alpha is the probability that the sum as I goes from 1 to n of the xi is greater than or equal to k3. This is the probability that 2 lambda sum of the xi is greater than or equal to 2 lambda k3, and nothing flips because the rate parameter for the exponential is definitely positive. This is the probability that, say, w is greater than or equal to 2 lambda k3, where w is 2 lambda sum of the x's. And we know that w has a chi-squared distribution with 2n degrees of freedom, and we want to be up above something with probability alpha. So if you envision the chi-squared, that's so horrible. You envision the chi-squared 2n PDF, that's also horrible. But we want a number that we are above with probability alpha, and our notation for that critical value is chi-squared sub alpha comma 2n. And this means that 2 lambda k3 had better be chi-squared sub alpha comma 2n. And this means that k3 is chi-squared sub alpha 2n over 2 lambda. So our final test, the answer here is going to be to reject, you know what, let me make this even more glorious. The best test of size alpha of lambda equals lambda naught versus lambda equals lambda 1, where lambda 1 is less than lambda naught, and we're dealing with the exponential distribution, is to reject the null hypothesis in favor of the alternative if the sum of the x's, nice and capital when you're giving this answer, is greater than or equal to k3, which turned out to be this. Chi-squared sub alpha comma 2n over, did anyone catch that? The x's are exponential with rate lambda naught, which means this should be a lambda naught, which means I should be multiplying by lambda naughts, which means this should be a lambda naught. Why didn't you stop me? And this should be a lambda naught, and this should be a lambda naught. And in the end, this should be a lambda naught. So we're going to reject if the sum of the x's is greater than or equal to the chi-squared critical value over 2 times lambda naught. After all, if I left a lambda there, how are you going to know what to do? We don't know what lambda is, so we can't make a rule based on having lambda in order to make a hypothesis test to determine what we think lambda is. So definitely a red flag popped up for me right there. I can't have a test that relies on me knowing the unknown lambda. And if you want to equivalently give this in terms of, like a sample mean, you can do that. You can divide both sides by n. We'd get the same thing even if you decided to start with the sample mean further back. But either one of these is the best test by the Neyman-Pearson lemma. So nice, right? It gives you the statistic and gives you the direction. And then the rest of it is identical to what we've done before. Okay, so next I would like to prove the Neyman-Pearson lemma. I'm not sure I'm going to finish it, but there are some things I can definitely say to get us going for next time. So towards proving it, I want to look at some notation maybe that will help us prove it. Maybe I have time. Let's go. Let's try it. Proof of the Neyman-Pearson lemma. Okay, any difficulty you might have in this proof is going to be purely based off of notation, and it's going to take a while to sink in. So just know that you're going to be okay. I'm going to let C star be the critical region defined by the Neyman-Pearson lemma, which said form that likelihood ratio and reject if it's less than or equal to some k. And I'm going to use the notation where the vector x is just all the data, x1 through xn. And again, I don't care that this is a row vector because I'm just using x with the vector on it to talk about all the data together. And I'm not actually trying to do any matrix manipulation here. So note that for any set A, and I don't necessarily mean the critical region, and I do mean some sort of n-dimensional set that I'm rushing, the probability that the vector x is in A when the parameter is theta, I used this notation at least once before. So I'm going to write an integral or a sum over A of the PDF with the parameter being theta. And this is a probability involving all the x's, a joint probability. So the joint PDF and then dx. This is shorthand for an n-dimensional integral. And then a dx1 out through a dxn. And then the limits of integration here have to describe the set A, which in general is hard to do. Okay, I said I had time. I have more time than this, but this is a good stopping point, I think. So, I psyched you out again. We're not proving it today, but we are ready to prove it. We are right there. And then after we prove it next time, we are going to move to simple versus composite tests and define most powerful tests or best test uniformly in the parameter from the alternative hypothesis. Next time on Mathematical Statistics.